Hello, my name is Hamidan Hafsa and I am a PhD student at the Department of Physics, Faculty of Science, Moulay Ismail University. So my presentation today is about an application analysis of adaptive neurofuzzy inference system strategy for greenhouse climate parameters prediction for internal temperature and internal relative humidity. For this aim, my presentation will be organized. I will start with an introduction in which I will give the aim of our work. After that, and as preliminaries, I will give a brief insight of the theory behind ANFIS strategy. Then I'll be sharing with you the materials and methods engaged in this framework. The application of the proposed strategy will be presented in form of two prediction cases regarding the internal temperature and the relative humidity. And to finish the presentation, some conclusions and future perspective will be shared. Being one of dynamic systems, agriculture greenhouses are considered as one of the most important agri-food segments, especially when it comes to plants and crops protection and appropriate indoor climate maintaining. The modeling part of greenhouses is somehow delicate. The nonlinearities between its different parameters makes it difficult to get to the appropriate model and the prediction of the climate parameters variation. In this sense, many strategies were suggested, and one of them, artificial neurofuzzy inference systems, considered as one of the artificial intelligence technique. So the aim of our framework is the prediction of internal climate parameters of the greenhouse shown in Figure 1, using ANFIS strategies, and more precisely the prediction of internal temperature and internal relative humidity. So as a brief insight of the strategy adopted here, an adaptive neurofuzzy inference system is a data-driven technique that engages fuzzy logic and neural network strategies to solve approximation problems of complex systems. In general, the structure of ANFIS systems is composed of 5 layers. Each layer contains nodes connected to each other with operator and functions. An ANFIS system is composed generally of 3 main processes: the fuzzification in the first layer, fuzzy inference for intermediate layers, and the defuzzification in the output layer. For simplicity, we took here the example of 2 inputs, 1 output system as shown. For more clarification, every input is decomposed to a fuzzy set, and the equation shown from 1 to 6 gives more detail about what happens in every layer. In addition to what it was already mentioned above, training algorithms take a leading role in generating an ANFIS system. Their role is to adjust the parameters of the fuzzy inference system and optimize consequent and premise parameters. Many algorithms are used in this sense. The most commonly used is the hybrid algorithm. This algorithm is generally generated according to 2 steps. The first aims to adjust premise parameters while fixing the consequent parameters using backpropagation of the error. The second adjusts the consequent parameters while fixing premise 1 using this time mean square method that aims to minimize the distance between observed and predicted data. And to validate the efficiency of the ANFIS system, some statistical functions are generated. For example, the mean square error, root mean square error, and the autocorrelation factor that are presented according to equations from 7 to 9. So for the materials and the method part, the experimental greenhouse used in this work is a greenhouse prototype equipped with 2 temperature sensors, 2 humidity sensors, and 2 actuators, a fan and a heater. To ensure the appropriate climate, both sensors and actuators are connected to an acquisition card related to a personal computer for data acquisition and control task aims. The most important steps for an ANFIS system identification are the training and testing steps. These steps permit to train the data and define the resulted prediction criteria. So here we take the case of the internal temperature prediction. The ANFIS model adopted here is shown with 5 inputs that are represented by external temperature, external relative humidity, internal relative humidity, and the actuator's action, the fan and the heater. And the predicted output is the internal temperature. For the whole dataset, we choose to work with the whole experimental dataset that is 2,200 samples. The training data represents 70% of the whole set with 1,540. The testing data represents 30% of the whole set with 660 samples. The same here for the relative humidity case. This time the input were chosen to be external temperature, internal temperature, external relative humidity, and the same actuators actions, the fan and the heater, to predict the output, which is the internal relative humidity. The same experimental dataset was adopted here with the same number of training and testing data. So here, the member function used here, or the type of member function used, is the grid partition with two membership functions. The optimization method used is the hybrid one. The number of training and testing data were already mentioned, and the number of iteration is 200. So here we have the result of the predicted and the observed internal temperature. For figure 4, we have training and testing processes for the whole set, while figure 5 represents the observed and predicted internal temperature. We can notice here that the internal temperature, predicted internal temperature, fit with a good accuracy the observed or real one, while figure 6 represents the root mean square error for the temperature case during training. Here we can notice that the error decreases to be settled to 0.38. So here for the relative humidity case, and as already mentioned for the temperature, internal temperature case, the type of membership function is the grid partition. The number of membership function is 2 as well. The same optimization method is the hybrid one used here. The number of training and testing data are the same, and the number of iteration this time is 600. So here we can notice that we have from figure 7 the training and testing processes for the case of internal relative humidity, while figure 8 represents the observed and predicted internal relative humidity. We can see that the same here as the internal temperature case, we have a good accuracy or a good fit gathering the predicted and the observed relative humidity. For figure 9, it represents the root mean square error for the internal relative humidity case. We can notice this time that the error decreases to be settled to 0.63 this time. So here, to conclude the results, the table shown here summarizes the different processes and their statistical functions concerning the ANFIS model of each climatic parameters. For example, for the first process, training testing for temperature, internal temperature, with its statistical criteria, and the same for the humidity case. So to conclude the presentation or our work, we can say that the prediction of internal temperature and internal relative humidity was guaranteed with a good accuracy using the ANFIS strategy. We can say also that The ANFIS strategy is an effective strategy to be considered for future work depending on our prediction aims. And as perspective, the application of this strategy for prediction of other climatic parameters is aimed, and the application of this strategy for other agricultural seasonal periods and with more data set is one of our perspectives. So thank you for your attention.